Hello everyone, October 14th. Alright, perfect squares, 279. Let's go take a look. I might have done this before. That's like every question I see, I feel like I have done it before. By the way, I just received an email yesterday about a challenge called IEEE Extreme. Dude, that one is crazy. That one is 24 hours. Solving, I think, 25 problems. Competitive programming, 25 problems in 24 hours. Maybe 26, I don't remember. I think in 2004, and last year, it was 25 problems. I took a glimpse. It was not like easy problems. So basically each problem takes about an hour, but it's gonna be 24 hours. I'm like, nah, I don't, I'm too old for this. I don't have the energy. I need to sleep. So yeah, we're just gonna stay with what we have right now. Alright, give an integer n, return the least number of perfect squares that sum up to n. Wait, hold. The least number of perfect square numbers that sum up to n, okay? So that's 3. Oh, but we can always say 1. Oh, it always works. Because in any case, you can always do 1, 1, 1, 12 ones, right? Or 3 4s. Or we can do a 9. And we have 3, so 9, 1, 1, 1 also works. 13, 4 plus 9. Ooh, interesting. Okay, let's see. Perfect squares, right? Can we find like the closest perfect square? That's not, I mean, we can limit. How do we do that? Square root. Square root the number and then square it. So we square root this will give us, let's do 12. Right? 12 square root will be 3 point something, right? So, and then we take the integer and then double it will be 9. So we know the largest we can have is 9. So we have a upper bound, right? So every perfect square from 1 all the way to this. Now we need to determine the least number of square numbers to sum up to. So what can we do? Isn't this like I don't know, least number of? So we have all these values, right? 1, 4, let's say 149, right? We have 149. We want to know the least number that we choose can add up to 12. So we can say, I'll pick 1, right? Then it will be the least number that can to reach 11, right? And then we can pick 1 again. But that's, if we pick 1, and every time we pick 1, that's always gonna be a lot. So let's go reverse order, right? So 9, 4, 1. So if we pick 9, right? If we pick 9, then we need to find the least number that can reach 3. And for 3, least number that can reach 3, we call the same function. Right now we find out it's going to be 1 because 3 square root is 1.7. Right? 1.732. So that's going to be 1. So we can only do 1. If we can only do 1, that's just least number is 3. So therefore, if we pick 9, the result is 4 numbers, right? So 9 is done. Now we say we're going to take 4. The largest value, we're going to take 4. If we take 4, the remaining is 8, right? Okay, so we need to find the least number that can reach 8. Now least number can reach 8, again 8 square root will be 2 point something, right? So the possibility is 4 and 1. So we take 4 again. I can take 4, or we can take 1 that take 4 again. And now we have 4. And 4, the least I can do is 4. And divide it with 0. And then, boom, we're done. So this one gives us 3. So that's smaller. Okay, so starting from 4, if we take the largest value every single time, yeah, that's it. Like if we take a larger value, we definitely reach the goal faster. Yeah, if we can take the largest value that we can take, and that's definitely the largest, okay? So that's that, and then we can say, okay, now for 9, let's say we take 1. If we take 1, then we have 11. And then we can only take 1. Oh, if we take 1, the largest we can take is 1. Because the larger we will have taken, right? So when we take 9, the largest we can take is 9 or smaller. So we can take anything below 9. But if we say 1, the largest is 1, that will require 12 numbers. So that's bigger. So the answer is 3. Okay. So can we... How about 13? But 13 will be 9 as well. So we have 9 for 1, right? And then we say, okay, we take 9. So we need to find the largest. We can turn 4. Yeah. I think we can write just memorization, cache. Or whenever we do cache, it's possible to do bottom up. How do we do bottom up? If we want to do bottom up, right? So think about it. Bottom up. You know what? Let's finish the top down first. Let's see if the top down works. If top down works, then we think about the bottom up. It's like if the top down doesn't work, then there's no point in going to the bottom up. I think the top down shall work. I don't see why it won't work. All right, so I don't need any of these. All right, so what we're gonna do for sure. Import cache. We're gonna cache it, and then I'm pretty sure it's gonna be here. All right, so we're gonna add value cache, max size equals none. All right, so what do we do? Oh, I should not do it this. I cannot do it here because I need to figure out the list. And the list, import math, right? So the list, so the list, perfect square is going to equal to, all right, this, list, actually we don't need, we just need the largest. The largest, yeah, we need the largest. So max perfect square is going to be max dot sqrt n, and then we're going to take the integer of this. Right, I'm going to take the integer of this. So this is the maximum possible. Now what we're going to do is we're going to def let's call it solve, right? So basically this will return the minimum number of of perfect squares that can add up to the target. So we're gonna have target, and then the max perfect square. Oh, passing a different max perfect puff square. It's called puff square. All right. So the max that we can take. Oh, that's not max perfect square. Max. It's a max square root actually. Max square root. So max square root, and then this is going to be max square root. Wow, can we name it differently? Max square root, and this is the individual. Every time we call it, And this one will return an int, right? And then this is going to be cached. Max size equals none. Alright? So this is going to cache. So what are we saying? What we're saying is we have a target and we have the max. Then we're going to say is for each one, right? So, do we compute it? Where do we compute it? Actually, we don't need it. I can compute it. The max square root I can compute at each level, right? I don't have to. I just need a target, and at each level. Then why do I need to initiate a new function? I don't have to initiate a new function. I think I can do it here. And then let's just call it max sqrt, right? Max square root. And then all we need to do is for, let's say, candidate in range max square root, right? So max square root to 1. And that is going to be -1, right? And then for each one of them, I'll say I'll take the current max square root, the candidate. I take the candidate, right? And then if I take the candidate, right? If I take the candidate, then I'll say the remaining, right? The remaining. So what do? We're gonna call res equals 0, right? Res is 0, and then actually res is not 0. Find the minimum, so res is max.inf, and then for each one I have the candidate, so we have the remaining value is n minus candidate. So we're going to find num squares, right? So we're going to say res equals min res self.num squares n minus candidate. Yes, n minus candidate. And that and the +1 because I used candidate already. So res equals this, and then we go through everything and we return res. But as a special case, we say if max square root, if max square root is equal to n, right? If it's equal to n, then we're going to return 1. So we already found it, we'll just use that and we're done. And if max square root is equal to 1, then we'll return n. Right? If the max square root is 1, like we're talking about 3, situation 3, then we just return this. Okay, otherwise res equals this, then for this. Alright, let's try it. Let's see, a test case will be easy to write. And it's jamming in terms of test cases. Let's do this first. 12 should be 3. 13 shall be 2. To see if these two pass. N. This one will be num squares n. Alright. Oh no, that is not correct. Vastly not correct. What happened? Oh, it's not candidate squared. Jeez. Candidate squared. Still, almost. We got one more. I feel like this should be 0, right? Hold on, I think again. I say 1 plus whatever the remaining. So if I go 4, right? And then and then self dot minus can will be 2 minus 4. Right, so 12 minus 4 is 8. 8 comes in, max square root is going to be 2, and now we go 2 and 1. So we go 2, and then 8 minus 2 is 4. Come back. Oh, max square root squared. Here, if it's squared, is equal to n, then we return 1. Otherwise, if it's square, that's 1, that's fine. Yeah, there we go. I mean, this one we can test lots of test cases because n all the way to 10, so we can just say 1, 2, 3, 4, 5, 6, 8, 9, right? And then 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 1000, 10,000. Alright, run this. Yeah, submit. I think this one's good. Oh no, what happened? Wrong answer. It's still judging. Time limit exceeded. What? Oh. The test case I picked is now good. 2278. What the hell? Wow. 88 milliseconds. What's the time limit? Gosh. Is it because of all the square root? I could be. That could be all the square root is causing the problem. What should we do? And then we can try bottom up or well, end it first, end it fast. And how do we know, right? How do we know? We don't know. We do not know. Let's try bottom up. All right, let's try bottom up. I mean, this one top down we have timed out. There could be many issues. Right, it could be just constantly doing square root. Basically, we do square root every single one, which is apparently not ideal. What if we list out, right, at the beginning, if we list out a list, let's call it a list of all the perfect square numbers, and then every time we do binary search. Huh? That's a thought. That's a thought. We can do binary search to know which one I should go for. Okay. Let's go binary search, which means I do. This is not going to be here. We're going to have to def another function. So def solve. Def solve whatever this one will require. But here, this is going to be. We can call it square list, right? Square list. Squares. Right? Squares and equal to list range. Ooh, list range. And be here. sqrt square for sqrt in range 1 to this plus 1. Yep, that's all the squares. Now with that, we can say from bisect, import bisect, we do bisect right. Yeah, the bisect right. So that's solve. Now when we solve, what we need is same thing as an n. It's a target. So we have a target, which is a int, and I'm going to return a int, right? And again, then we use a binary search. Oh, would binary search be? I don't know, but basically when a binary search the target, right, and see if, so I'm going to say index, right, index is going to be bisect right squares and target, and we say if index, so it will not be smaller than 1, right? So it will be just in between. We say if target, not target, if squares, I spell it wrong, it's Q-U-A-R-S, if squares index minus 1 is equal to target, right? Then we are going to return, if it's equal to target, then we're going to return n. No, we return 1, right? If it's equal to target, then we're going to return 1, right? And if it's equal to target, we're going to return 1. And if squares index minus 1 is equal to 1, we're going to return a target, return target. So we have these two out of the way. Then for candidate, now it's a candidate, it's going to be for I in range. So we're going to go from index, right? From index all the way to the start minus 1, right? For I in range index minus 1, rest equals mean rest self.num squares n minus squares I plus 1. And then we're going to call, we're just going to return solve n. Oops. List index out of range. How is that possible? Oh, index minus 1. Index minus 1. Okay. Or will this make it faster? I actually don't know. I don't think this will make it faster. It's 88 milliseconds. Oh, this one is much slower. Wait, what? Wait, they had an infinite loop? What the hell? The previous one worked on this, and this one does not work? Yep. Then we hit an infinite loop. Hold up. Why would we hit an infinite loop? N minus. hold on, let me think. So I minus this value. Oh, n minus target. Well, how does it still work for this? What? Still not good. No. Yeah, it is target minus. The target minus is still not right. Oh, num squares. Solve. And it's not self.solve. There we go. Well, I'm not very confident about this one. Early one is 88. 48. Ah, this might be the case. Oh my god. Oh, it did pass, but with very, very bad runtime. Oh my goodness. Okay, so the problem is with the square root. Square root takes too much time. And by eliminating square root, we swap in the binary search, and it passed. But with very ugly time. Look at that. Look at that. 6 seconds. I was almost giving up hope. I'm pretty sure there'll be some, like right here, 100, 200 milliseconds. Yep, look at that. Holy guacamole. We're all the way down here. Good solutions are, what? 50, 40, 20, 20. Oh my god, 20 milliseconds. Mine is 6,345 milliseconds. Wow, it's the best description of my name, right? It's really mediocre. So the initial attempt, TLE, which I think was due to the use of too much SQRT operation. Thus, in this version, we pre-compute all the possible perfect square candidates, and then use binary search to determine the largest, right? The largest each subsequent, the largest one, largest perfect square each subsequent target can use. I mean, there's no early stoppage, that's the thing. Early stoppage. We can do early stoppage. So if we hit a value, if we multiply by the current value, if multiplied by res is smaller than we don't have to do it anymore. Optimization here. So we say if, all right, if res times squares I, right? If res times squares I, which is the current biggest that we're looking at, and if we times all res is smaller, right? If it's smaller than our target, then we're gonna break. That means it's not possible to get even better performance moving on. Look at that. It shrank to 99. All right, let's not write this yet. Yeah, let me just do all this, and we're gonna run again. Hold up. I need to put somewhere. Okay. All right. So this is a key step. I think this is a key step. So run this one again. 227. 39. Yeah, we did. We'll get even better. So let's see. Look at that. We shaved off from 6,345 down to 538. Right? That's 10 times faster. 10 times faster. It's 2 lines. 2 lines we get it 10 times faster. That's more like it. Right? That's more like it. And I think if we do bottom up, it can be even faster. It can be even faster. But hold on, let me finish writing this one first. All right, the initial, which I think was due to blah blah blah. In this version, we pre-compute all the possible perfect, and then we can use binary search to determine the largest perfect square each subsequent can use. Then comes the key trick. We can stop searching early if the current if the result we have found, if we can be sure that the result we have found so far is already the best we can get. Now, how do we do that? To evaluate this, we always check the perfect squares from large to small, right? Always large to small. And for each large perfect square, we can obtain the minimum number of. We can obtain a result, right? We can obtain a result. Then, for the next large perfect square, we can multiply it with the result obtained previously, right? Previously. If the product is smaller than our target, that means even if using only this large perfect square, we cannot reach our target. Thus, any further search is futile, right? Because we're already using the largest that we are allowed to use so far, and then we obtain the result from previously, and then we multiply that. So if we use only this largest and we still cannot reach our target, then it's futile, which means if we use even smaller ones, then we cannot reach for sure. So thus any further search is futile. And we can terminate rather, right? We can terminate rather with this trick. With this trick and the use of binary search, actually, no, it's fine. And the use of binary search, we obtain runtime at 538 milliseconds, or what's the ranking? 74 or 74% ranking. What's the time complexity? This takes square root n to produce. How about the solve? I don't know. I mean, I don't know, because each time I minus someone in, I mean, the worst case scenario is we go through every single one, right? We go through every single one, so it's O square root n, and because it's cached, so each one's only visit once. Yeah, I do think every single one is I'm gonna throw O square root n, and my rationale is to create squares to take O square root n, and then from target going down, and most will take away every single one in the squares, right? Every single one in the squares, and that takes O square root n. So I think time complexity is O sqrtn. I'm not sure. Not sure. Now the question now is, can we do bottom up? If we want to do bottom up, take a look at this. I have to go through every single one. That would be ON, right? All right. Cannot see the solution, which is fine. Let's look at the smart people. What do the smart people say? Yeah. 279. What do the smart people say? Yeah, I don't think I've done this before. No. Smart people say DP, easy to understand. Oh my god. How did you create this? Did you write this? I don't think so. I think this is printed. Oh, I think this is bottom up. ON square root n. Uh-oh, I got it wrong again. ON square root n. Yeah, every time like the top down is really hard for me to figure out. ON. Note, time is ON square root n. I got it wrong again. Alright, let's take a look. Array of size n plus 1. Okay. First iteration. We construct every number using perfect square 1 only. Second, we put 4. Next perfect. So, which is minus, minus 4? Oh, we use 4. So if we use 4, then this one will be 1. We use 4. Oh, that's the... Wait. This is 4. Plus use 1. Give us 7. And if we do 4, that means we can minus 4. Oh, minus 4 plus 1. Minus 4 plus 1. Minus 4 plus 1. Not minus 4 plus 1. This is minus 4. That's 3 plus 1. And then this, how do you expand this? This is all... Hold on. It's divided by 4. Right? We divide it by 4. That's the number of 4 you can take. So we divide it by 4. We get a integer division. And this one minus... Then that's just... right? So divided by 4, we get how many 4 we can take away, and then we do that times 4, and a minus, that's a remainder. So it's going to be the remainder plus the quotient. Remainder plus the quotient. So the remainder plus the quotient. So the remainder will be 1, the quotient is 1. Remainder is 2, quotient is 1. Remainder is 3, quotient is 1. Remainder is 0, quotient is 2. Yep. It's the remainder are the ones that we can do using 1. Now, if we do 9, so we can start from 9. Again. We can do... we can do remainder, so we do 9. Also remainder plus 1. And then we compare to the previous one. We'll take the smaller value, right? Yeah, remainder is 2 plus 1 is going to be 3. Remainder is going to be 3 plus 1 is going to be 4. But when we use 4, it is smaller. Therefore, 3 wins. And we just keep going. Oh, nice. Wow. This is wow. Oh yeah. Yeah, it's the same idea, right? It's the same idea. We always start using the maximum you can use and see how the remaining is gonna go. But just every time when you use a bigger value and the remaining we use the maximum number of big values we can use. Yeah, we always use a maximum big value. I think that's the case. Like if you want to make this, we can say we're going to take the maximum out, which I think this can be even further simplified, right? We take the maximum that we can take, and then the remainder, we'll find the remainder. Because every step, if we take the maximum out, and we'll have another one that allows us to take the maximum out again. If we do not take the maximum out, we take the smaller one, right? If we take the smaller one, then it will be that a couple smaller ones will add up to the big one, right? And then we're just wasting. It's like greedy. It's a little bit greedy here. If we don't take the max, then we take the second max. Let's say the second max, right? If we take the second max, then we'll take a couple more to add up to the big one. Because we're trying to say, let's just say that. Let's say if we take the second one and we achieve the smallest, right? And then it is possible to combine those, to combine some of that, and we can reach a value that will reach the big one. Yeah? Does that make sense? Yeah, it does. Or we can like combine some value which is bigger than the large one, and we can take the bigger one, and then yeah, because the small one, two of those small ones will always be smaller than that. So at least we need to take two of the small perfect squares to equal to a bigger perfect square. So like, yeah, and then we're wasting. Which means I think here we can do better. So it's the same idea but greedy. Right? So solution 2 is the same as solution 1. Same as solution 1, but with greedy. That is, at each time we only take the largest perfect square that we can take at the moment, right? We take as many largest perfect squares that we can take as possible at the moment. This works because if we can take a large perfect square, it is always better to take that instead of taking multiple smaller perfect squares. So in this case, this is all good, this is good, this is good, these are all good, right? And actually, we probably don't even need this because we can just say if what do we say? We say we have the square, so we're going to say QR equals div mod target squares I, right? First of all, this one I think still applies. And then we do div mod. And then if R is 0, right? Res equals min res q. Else res equals min res, when I solve again, and target minus this is actually just remainder, right? It's going to be remainder plus 1. And then I think in this case, this can be contained, right? Because we don't need this. And we can say if not target turn 0, I don't need all this. I have the index and blah. And then if res is smaller than target, we're going to break. And QR equals this. And we don't need to do this. We can just wait, hold on. That's not plus 1, that's plus Q. Right? And then plus Q. Let's see, solution 2. Okay. All pass. Let's see if solution 2 is faster. Oh man, it'll take a long time to load. Alright, let me go to submission again. Okay, so again we do this div mod, and then we do this. If it's 0, it may return. Yeah, let's see if this one is faster. Oh, a lot faster. Wow, this one is a lot faster. Yeah, time compressed. It's actually this is more than n times square root n. But this one is a lot faster. We're clocking at 160 milliseconds. Or a 92. It's not ranking. So greedy is the way to go. All right, solution 3 is bottom up. So 3 is bottom up DP, courtesy of this. Very nice explanation there. All right, so for this to work, we need to have a DP table, which is going to be list range from 1 to n plus 1, right? So that's our DP table. And then what we're going to do is SQRT is going to start from 1, right? I'm going to say while SQRT is smaller than n, smaller equal to n actually. If it's smaller or equal to n, that's where you just keep going, keep going, keep going. We're going to find the last one. Right? If it's smaller or equal to n, then for let's just say for I in range, right? For I in range SQRT squared all the way to n plus 1, right? For I in this, then we don't need to start with 1 because this is already started with 1. Let's start with 2, right? So for I in range this, and then DPI, right? DPI shall equal to minimum DPI and div mod. We need div mod. So when the QR equals div mod I SQRT squared. Too many times we're calling it squared. Perfect square equals SQRT 2. So call it perfect square and perfect square, right? So div mod that. That simply means we need to take Q and then remaining R, right? So it's going to be Q steps plus DPR, right? R is the remaining, and then remaining will always be computed before as the minimum steps that we need to take would be DPR. So the minimum steps going to take at DPI will be a div mod, the current perfect square that we're looking at, div mod. So the maximum we can take out of the perfect square right now is Q, and plus the remaining. So we go DPR, which is the number of perfect squares needed for R. And then looking by these two, we take the minimum, and this one will go all the way to the end. Every time we do one run on, another run on log on square root n. Yeah. So we do this, and at the end is QRT plus equal 1. All right. What can reduce this? SQRT equals 2. Perfect square is 4. I can directly go here. We say PS is smaller or equal to, no, we don't need this. Right? And then PS equals SQRT times 2. Right? And now when we're done, we're going to return DP, the last one. Okay, so 3 Ooh, index out of range. What the hell? How is index out of range? I in range. Yeah. Oh, we have no DP0. Oh wait, this is wrong. DP, we need to have 0. So 0, 1, 2, 3, blah blah blah, all the way to n, right? And then there we need a 0. Not 0, like if it's 1 to this, we don't have dpn, but we require dpn. Alright, let's try this one. I expect this one to be even faster. Alright, try it. No. I think we might... Wait, what? Oh, I think we forgot to handle... Wait, hold a sec. Yeah, I think we forgot to handle the early breakage situation. Alright, perfect square is the current perfect square, right? So every time before we start, I need to check. We say if perfect square times dp minus 1 as number of steps, right? If perfect square, hold on, no. Probably don't have. Yeah, we go all the way to the end, we go all the way to the end, we go all the way to the end. When do we stop? We go 4, right? PS is 4. And then the next one. And every time Wait, what did I not notice? Well, minimum I minus SQ a square. But this one's so much faster. We did have to go through every single thing, that's true. Well, the smaller 0, and we have this, and then for I and this to this, dpi, minimum dpi, and then we say I minus, yeah, it's the same, I minus this plus 1, that's fine. Actually, it's not fine, we have a div mod. Maybe that one causes time. Okay. Try not to do div mod then. Yeah, it's the same. Like we say, we take. Yeah, okay. Yeah, it's actually make more sense to do dpi minus perfect square, right? So if I minus perfect square is going to be I minus perfect square is the previous value. So it means we take perfect square right now, and we're looking for what is the maximum previously, and this one plus 1. Okay, try one more time. So we get rid of the div mod. Square should be fine. Okay, try this. Nah, no, I don't think that's the issue. It shaved time in half, but compared to this, that's just... Because this one I have a early breakage. Yeah, that's the problem. This one, which starts from bottom up, right? This is bottom up, true bottom up. And because we're doing bottom up, we have to go through every single one. And this is greedy from top down, so we always take the bigger one already. So if we find it already, then we can break it. And this one we cannot. We have to go through every single one. There's no way we can break early. So we have to go through the small one. Now this one, we don't have to go through the small one. Yeah, that's the difference maker. Yeah. However, this method is slower than solution 2, right? And solution 2, because with bottom up, we have to go through all the small perfect squares, whereas in solution 2, we have a condition to stop searching early. Yeah, that's why this one is... I think somebody must have... But this is a good solution. Yeah, this is a good one. Brute force... Oh. Legendre's theorem. According to Legendre's theorem, every natural number n can be represented as a sum of 3 squares of integers, if only if n is not of the form where n be in the negative. Oh. Wow. So we check this first. Wow. No. Dynamic programming, brute force to optimum. Top down, bottom up, log around. We can do this. Too lazy. Actually, we can and let's submit ours. Top down, DP with greedy, right? How about that? So let's say 3, top down, DP, greedy, and I'm gonna combine both. I want to combine both. How do we do this? Okay, so I'm gonna get into a new text editor, right? And then I'm gonna use this, right? Use this. And then we do a little bit modification. We pre-compute that. We don't need to describe the pre-situation. So we pre-compute all the possible blah blah blah. Largest can use. Trick. We can stop early, right? Smaller than means even. Okay, yeah, we can do this. And another trick. Also, we can use greedy. That is, each time we only take as many largest perfect squares that we can take, as many largest squares as possible. each time we take as possible. This works because if we can take a large perfect square, it is always better to take that instead of taking. All right, so this one give us this. Okay. All right. Da, 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 da. Post. All right. That's it for today. Good. And we solved it and we improved our solution. I'll see you guys tomorrow. Adios.